before we begin, I want to remind you of the derivatives because we're going to go through this section relatively quickly. Power rule, so easy to use. Take the derivative of a constant, Actually, why don't I just use C, right? A constant, you'll get 0. Take the derivative of a constant times x, and you will get that constant. Take a derivative of x squared, and you will get 2x. Now, I could throw a constant in there if I wanted to. I could say, oh, there's a constant here, and oh, that constant would still be there because you notice in the previous rule that happens. But I'm too lazy to do it. I can't even write it properly, so I'm gonna keep going without constants now. Take the derivative of x cubed, and you get 3x squared. Take the derivative of x to the 4th, and you get 4x cubed. Take the derivative of x to the 5th, and you get 5x to the 4th. And take the derivative of x to the 6th, and you get 6x to the 5th. And I'm saying, yes, you should write this down. Pause and write it all down. Remind yourself of all of these derivatives. Get it to a habit to where you could just take these derivatives as quickly as I am, okay? So here's your reminder, and pause the video. Now, when we get into here, hopefully we'll find that we're going to be way on it when we want to take the antiderivative, meaning if we want to undo derivatives, okay? So this first one, he's trying to do the same thing as I was trying to do, which is to remind you how to take the derivative. So now you could pause the video and just take all of these derivatives. Hopefully, this is what you got. And you notice that I actually write down the zeros. Did you? I'm still in the state where I like it. I keep getting interrupted when I'm trying to do a derivative. I've got kids, or I'm in the classroom and there's kids. And so I just always write it down to help myself later on. I know that I don't need those. And hey, what did we notice here? What was the discovery part of this? The discovery part of this is that constants are lost when you take the derivative. Okay? And so he says, what should I get when I take the antiderivative of this? Well, I should definitely get this, x cubed, right? Because the antiderivative of 3x squared means undo the derivative that I took. And so off to the side here, where do I see a 3x squared? There it is. And how do I go backwards? I go backwards like that. But here's the deal. Did we notice that those constants were lost? We should say that we have to bring it back. That constant's important, you know, we should bring it back. It's a thing that we need, all right? So now he introduces to you this symbol and that notation, which tells you what? It's called the integral symbol, and it tells you to integrate or anti-differentiate this expression. The expression is called the integrand. So just this little piece is the integrand. It's the thing that you are integrating. And the dx tells you that you are integrating with respect to x. It doesn't really affect the integration process at this point. Later on, when you go to a higher level of calculus, you might see two integral symbols, and then you might see a function with an x and a y, and then you might see like a dx and a dy. And it turns out that what you're supposed to do is you are supposed to calculate this integral first and then that integral. So right now we're just going to stick with one letter. Okay, thank gosh, right? It's calc 1, so we don't have to do this. This is business is for later. All right, so for us, for now, we just write that dx down and everything's good. Now we take a look at the integration rules, and I'm saying that they seem kind of weird. particularly this looks pretty simple and that looks really complicated. So just the first rule seems, harsh, difficult. This rule, the constant rule, we're going to find it to be not that difficult. So let's give this a try. All right. So I'm wanting to do these off to the side here, and I'm actually going to write them by hand because it's going to help me when I think about it, and I particularly want to be able to use these reminders, right? So number 4, I have the integral of x cubed dx, and I highly recommend that you practice making that symbol. It's got to look not like an S. It's got to look like a long, skinny snake, okay? It's important that it be bigger than anything else, and in fact, why don't I go ahead and put down some lines here so that you guys can see that I'm making sure that that integral symbol takes up more than one line. It takes up more than one line on my paper, and I highly recommend that for you as well. So I'm looking around, and I'm at my little reminders here, and I'm hunting around for an x cubed. Does that make sense? I want to find an x cubed, and I found it right there. And I'm pissed now. Am I allowed to say that? I'm very angry now that there's no 4 in front of it. Why isn't there a 4 in front of it? Well, it could have canceled out. Let me imagine a situation where it would have canceled out. If I took the derivative of x to the 4th over 4, then I would see that I would get that 4x cubed on top. But on bottom, I would still have that 4, right? Because this is the same thing as a 1/4. Here's a 1/4 being multiplied by my x cubed. Another way I could write that would be there's a 1/4 being multiplied as a constant. And so then the derivative of x to the 4th is 4x cubed. In any case, these 4's cancel out, and that's how I get just an x cubed. So I'm wishing desperately that there would be a 4 there, and then I'd know what my antiderivative was. But I think I've got a hint. If there was a 1/4 here, then I would get the answer would be an x to the 4th here, right? I'm antiderivating. I'm taking the opposite of the derivative. So notice how this power was 3. It should go up to a 4. So the power goes up when you do the antiderivative. And am I allowed to just add a 1/4 here and then just get the derivative that I want? Oh, absolutely not. I know you know that that's not kosher. So I'm going to put a 4 out in front. Wait, what? So look at it. I mean, I did 4 times 1/4, and that's the same thing as 4 over 4, which is the same thing as 1, right? So those cancel out, basically. And how you write it, it's totally up to you. You could do it like this. 4 times 1/4 times x cubed. There's your dx. You could say, put these together in that order, and then say to yourself, okay, well, now I know this piece is just going to be an x to the 4th, and then there's still a 4 out in front. But I wasn't really trained to do that, and in his textbook, his notes, his answer keys, you'll see that he's not really trained to do that either. He likes it when this 4 right here comes out in front, and then you just have it be part of your work that you do at the end. And we're going to do it this way over and over again, so we'll be happy. Now, the last step, always, the last step is to put that map plus c. We don't know what the constant was. It got lost when we took derivative. And so, we have to write down that there could be a constant there and that we just don't know what it is. Now, eventually, we are going to learn how to find that constant, but we're going to need to be given some sort of initial conditions, and that would help us find that constant. And for now, we're just going to practice the antiderivative. So let's try that again. We've got a question number 5 here, and this is the integral of 2 with a dx. And I'm thinking about my notes, and I'm going back and I'm looking. I'm seeing, I don't want there to be an x value in anything, so none of those are correct, and I already know that this one's not correct. So I just want to say, when do I just get a constant as an answer? Boom, I'm going to call that a c. That's just a constant. That's my answer. So if I want to go backwards, what would I get? I would have had something times x. So my answer here is going to be 2x, and then plus a c. And I know right now this feels awful. You know what I mean? You're like, this isn't working for me. I'm not sure I understand what's happening. All right, let's try this again. If I make a table of derivatives, this is my function, this is its derivative, and I'm saying this is my f of x, and this is my f prime of x. When I say that I take the derivative of 0, I get 0. I take the derivative of a constant, I get 0. When I take the derivative of a constant times x, I will get constant. If I take the derivative of x squared, I will get 2x, and I think that what will help is if you say to yourself, this is the antiderivative, meaning that this is my function and this is me integrating it. Okay? So hopefully that method of writing down what the function is and what the antiderivative is will help just a little bit better. And for this last example, you could see that I was doing this, that I had a constant and I'm just going backwards and I'm saying that I get that constant times x. And now I'm going to say, and you notice that I've done these derivatives twice now. I really think you should write all these things down. If you haven't, pause and do it. So now we go to question number 6, and I'm doing it now looking at this table. And so I'm going to say, here's my number 6, and I have the integral of t to the 4th plus 2, and there's a parentheses here and a dt. And you're like, ooh, what does all that mean? Well, technically it means do the integral of t to the 4th and do the integral of 2 dt. Oops, did you see something I did wrong here? There it is. Turns out the graders expect it. They totally know it happens. You will not be marked down. They know you're in Calc 1, okay, and you're not integrating with respect to x, and so they just overlook it. It's not a big deal. All right, so right here then, I want to look for that t to the 4th, something to the 4th, and ouch, look at this table. I didn't even have that one written down. There we go. And so I'm looking for something to the 4th. I have that. And there's that lovely 5 in front. So I want there to be a 5 here, which means I want there to be a 1/5 there, because I'm trying to only add constants that cancel out. Okay, and so I wanted there to be a 5. There wasn't a 5, and so I made it. And now I know that the antiderivative of this, the 1/5, will still be out in the front, and then that 5t to the 4th is really the same thing as a t to the 5th. And then I'm going to look at my constant rule again, because I'm just integrating a constant, and I'm going to say that my constant rule says that I'll have a 2 and a t, and then don't forget that plus c. Always, always, always don't forget that plus c. Now, there's a lot of kids who get really upset about the idea of this hanging a equal sign. There's nothing in front of it. What do I put down? Do not do that. You are not allowed to do that. If you really must, if you are compelled to put something in front of that equal sign, make sure it's the whole integral. Do not say that to me that you did part of an integral. Because if you said like this, oh, well, the square root of something is 3, I'd be like, well, you need to tell me that the square root of 9 is 3. Okay? That integral symbol is an operation. It is not a label. Okay? It's an operation. It's something that you're doing to each piece. So if you want to, you really can be lazy and just try to line your equal signs up and just leave this front part blank. Okay. Now let's take a look at number 7, and I'm seeing there's an integral symbol, and it's a 2y squared plus a 4y plus 1, and here is my dy. And I'm saying that for a little while here, I want to break each one of these guys up so we can see each one of them individually and tackle them individually. All right, and so I'm looking for something that gives me a y squared. That gives me a y squared. So I'm wishing that there was a 3 in front. I'm desperately wishing that there was a 3 in front. There isn't one, so I'm going to add it. And then I'm going to put this 1/3 out in the front. Now, I know that this 2 right here has got to come down. I know that this 1/3 is going to come down. And this 3y squared, take a look, it turns into just a y cubed. Okay? And I'll put that all together as a 2/3 y cubed. Now I'm going to say that I have a 4y dy. So the hidden exponent is a 1. That's a hidden exponent of a 1. I was wishing that there was a 2 in front. So I'm going to put a 1/2 out in front. And that 1/2 is going to come down. This 4 is going to come down. And the rest of it, this 2y, gets turned into just a y squared. And that will be 4/2, which is the same thing as 2. And why did I put an equal sign? That's supposed to be a plus sign. 2y squared. And then here, the constant, the derivative of a constant, I took it, I got that constant. I must have had an original ready. I must have had a 1y. And then that last constant that I don't know what it was because it disappeared. And this is my final answer to that. So I think you can see that if the constant is missing, the pattern here that we want to recognize is that we want to throw that missing constant out in front. I don't know why I highlighted that too. Sorry about that. So I want to throw that missing constant out in front, and that'll help me with the rest of the problem. So now that we've done enough of those, hopefully we won't need to do that anymore. But I do know that this next one is a bit more complicated looking. So let's work on it. All right, let's work on it. So this is number 8. And it says that I have the integral of 3 over x squared. And I take away 1 over the square root of x. So what I'm wanting to remember before I do this is, and here, let me write that. Those are both negative exponents, okay? So I'm going to get the integral of 3 with x to the negative 2 power and a dx. And I'm going to get the integral of x to the 1/2 power, and it is negative. Little bug on my screen. Okay, and now I want to take the antiderivative. Well, this is a troublesome thing, isn't it? Because I look at this table, look, there's no negative exponents anywhere. I think negative exponents would be, up here, right? So how do I use then this rule? We've got the rule. How do we use it? Because right now, I've been teaching you how to use just that table. And the rule, what is it? How do we get it? Oh, how does it work? Here's what I'm going to do. I'm going to say that I just want to go through one little example where I remind you the integral of 3x squared. We know that when we took the derivative of x cubed, we ended up with that, right? We ended up with that 3x squared. Oops, there's a dx that goes right here. So if I want to kind of think about this rule, notice, what is that power? Well, that power was a 2. And he says, add 1 to it. Well, this power, if I add 1 to it, I will get a 3. And then he says, put that power in the denominator. You're like, well, you didn't do that. No, that's true. I didn't. And here's why. Ready? Because really, if I was showing all of my work, I would have done this. I would have said, well, there's a 3, and that's a constant, and so I'm going to write it down. Here's my n, that's 2. Here's my n plus 1, that's 3. And then right here, this was x squared with the dx. I'm just writing down the problem there. But now I want to put together my answer. Ready? Here's me putting together my answer. X to the n plus 1 is going to be 3x cubed, and it's over the n plus 1. But here's the thing. There was already a constant there. Oops, and n plus 1 is supposed to be, what is n plus 1 supposed to be? It's supposed to be a 3. And then there's a plus c. So the 3's canceled out. Ta-da! And my answer, my final answer will be x cubed plus c. All right? That's how we're going to use that rule. Now, do you need to memorize this rule? Oh, heck yeah, you do. Absolutely you do. Particularly this part right here, where you cannot take the antiderivative when n is -1. That is a special antiderivative. We'll talk about that one later. So here I am then, and I'm actually going to use the rule. So remember, the rule is that you have x to the n, and then you will get x to the n plus 1, and it will be over that n plus 1. You remember that piece. Here's the thing. Do you remember the rest? Do you need to copy this 5 times? I don't know, because this notation here, here, and here, if it's missing, you will be in trouble with the AP graders. I said you're allowed to accidentally change the letter. Like if I'm doing T's, I'm allowed to turn that into an X on accident, but I'm not allowed to leave it off. I'm so sorry. The graders need it to be there. So yes, you probably do need to copy 5 times. Let's ask me about it in class. All right, so now how do I go about actually doing this then? So I have this constant right here. That's a 3. Don't forget it. And I don't have a constant there, so that's a hidden 1, and it's kind of boring, so I could probably forget it. So now I'm going to say that my integral, let's take a look at this. I'm going to say that I do have a constant to worry about, and so I'm going to put it in my answer now so that I don't forget. And I'm just bringing it straight down. And then I'm saying that n was a -2, and so n plus 1 means -2 plus 1, which is a -1. And so I can say that my power x to the -1 is over n plus 1 is going to be that -1, and here is my plus c. And so what, well, there were 2 parts here, so let me finish with a grand plus c, because I still want to do this one. And n was equal to -1/2, and so n plus 1 is going to be equal to -1/2 plus 1, which means that I will have, ready, x to the +1/2, but it will be divided by this +1/2. Oh, how do I clean up this mess? Well, this is how I clean it up. Ready? I have a -3, and the x is in the denominator, and that 1 is positive now. So really, I don't have to write it down, okay? I wrote it down. You can write it down. It's up to you. If you want to leave it there, that's fine. The next piece is that when I look at my hidden invisible constant, which I forgot to write down, I will now have this 1 divided by 1/2. This piece right here is 1 divided by 1/2. And we're going to break out that, like, you know, I don't know. It must not be 5th grade rule, because my daughter is doing 5th grade math with me, and I haven't seen her do anything like this. But she's supposed to, you know, at some point, you're supposed to know that, you know, nested fractions, you break them apart, and you turn them into multiplication problems. Do you see where you flip those? And, you know, probably 5th grade teacher doesn't know how important this is in calculus, didn't really make you practice it much. I will be making you practice it a ton. Ready? That's going to be my answer, okay? And then plus that c. And what was I doing originally was this integral. And so notice how I have this equal sign here, I have this equal sign here, I have this equal sign here. This is a rule, and it is just, I moved it over to where you could see it, but it's not actually part of the problem. And this is me calculating my ends, okay? That's all, just calculating my ends. So now, if I want to, I know it looks a little bit messy, but I'm totally just allowed to put a box around it, okay? How do you know that you did it right? Take the derivative again. If you take the derivative again and you get this as an answer, then you've done it correctly. Okay, so now that we have done this, I will mention that technically speaking, you are allowed to leave that as an answer in a free response question, but this is your multiple choice answer, and so that's where we're at. If we're looking for that multiple choice answer, then that's what we would see. All right, so number 9 then, let's take a look at it. This is the integral of the square root of x plus 1 over x squared dx, and calm down. You can do this. I haven't taught you a quotient rule for antiderivatives, right? Right now, we're just working with derivatives. Antiderivatives, just straight, polynomial exponents sort of stuff. So is there a quotient rule for the antiderivatives? Technically, no, there isn't. There is kind of a product rule, and so you kind of turn quotient rules into quotient problems into product rules. We'll show you that later. It's called integration by parts. But for this, I'm telling you, this is way easier than you think. This is x to the 1/2 power over x squared plus 1 over x squared. And there's a dx here, okay? And these powers can be subtracted. You're like, I don't remember that rule. Yeah, I know. Here we go. If I have x to the 4th over x squared, I will say that I have x to the 4 minus 2, which is going to be x squared. So if I have x to the 1/2 over x squared, then I can just take that half and subtract that 2, and that's the same thing as taking a half and subtracting 4 halves, and so that ends up being, ready, x to the -3/2. Okay, yeah, it's ugly. It's not pretty. I didn't say it was going to be pretty. I'm just saying you can do it. So now here we go. We have the integral of x to the 3/2 and plus and it's a -3/2, and plus x to the -2 power, and there's my dx, and actually let me do it like that. Now, I'm missing those constants that would be out in front, but actually in this case it makes me happy because I don't really want to deal with them anyway. So n equals -3/2, and then I say that I have n plus 1, and that would be -3/2 plus 1. Okay, hold on a second. Now, you remember how I just said that I was missing some constants, and so I don't have to deal with that, and it actually made me happy? Yeah, let me recap. This rule right here, this rule is, I'm trying to zoom in on it. It won't let me zoom in on it. It won't let me zoom in. There. This rule right here is missing the idea that there could be a constant right there. So let me mention what the rule would be if there was a constant. So c with x to the n and a dx, I should still have a c in front, and then I should have an x to the n plus 1, and this would be over n plus 1, and then plus a big C. This is a little c. This is a capital C. Okay, and when it's missing, if I wanted it to be there, I would have thrown this 1 over C out in front, and then I would have a 1 over C here. Well, they cancel out, so that's why he didn't write it. You see? That's why he didn't put it in this rule at all. Why am I mentioning it? Because between you and me, we will get confused from time to time. When there is a constant and that's the only thing that's missing, when I'm dealing with a simple problem like this one, I want to use this little shortcut of just throwing a constant out in front and then having that reciprocal constant be inside so that I can take that antiderivative in the way that I wanted to. Well, okay, so now I'm going back and I'm saying down here, I don't have to deal with constants. It's in the power rule. It's in the antiderivative power rule. I'm taking care of it as soon as I write this. Ready? My derivative will be, what is negative 3/2 plus 1? It's negative 1/2. And so I say that I have, ready, x to the negative 1/2 power, and I'm dividing by negative 1/2. That's where I take care of the c. Okay, and then I can say that I have this, and n equals negative 2, and n plus 1 equals negative 2 plus 1, and so I would say that that would be a negative 1. And so I have x to the negative 1 power, and it is divided by negative 1, and there's plus a c, and don't forget to write that down. It's very, very important. So here's number 9. I'm finishing it up. I'm cleaning it up, and I'm saying that I have 1 divided by negative 1/2, and that will end up being, ready, it will end up being 1 times negative 2 over 1, which is the same thing as negative 2, and so I have negative 2 x to the negative 1/2 power should be dropped down at the denominator, and that's the same thing as the square root. Here, this will be 1 divided by negative 1, which is the same thing as 1 times negative 1, which is negative 1, and so I end up with a negative 1, and it should be over an x to the 1, which you don't have to write down, and then a plus c, and that will be your answer. Yeah, that's kind of rough. Nobody wants to do all that kind of work. We've done 9 of these problems now. Is there a way that we could do these without having to do all of that work? Yeah, I mean, at some point you're going to get a handle on just adding 1 to that power and then dividing by that new power. And here, even this piece, you're going to get a handle on it. If you have 3 over 1/2, I think, if you practice it a little bit, you'll notice that what happens is that this and this will end up being multiplied. Will end up being multiplied because you flip that fraction. See, you flipped it, and so now it's on top, and you get 3 times 2 is a 6. And so if I had this, then this will really be this. You see what I'm saying? If I had this, well, you might want to think about that one. Just right? It's going to be 6 times 3 is 18, divided by 2 is 9. I can show my work. 6 divided by 2/3 is 6 times 3/2, which is 18 divided by 2, which is 9. You see? So even these guys, you're gonna develop that habit, that pattern, and you'll be able to move on from there. Let's take a look at the next piece here. Let's take a look at it. Put plus c when you integrate, but never when you differentiate. Sometimes an initial condition is given, which makes it possible to solve for c. Hey, I told you we were going to be able to find that c at some point. It turns out this is that moment. Okay, so if I want to find f of x, I need to integrate this. Yeah, no, I'm adding that notation. I want you to see it. That the integral of a derivative will be the integral of that function. Okay, and now I'm going to actually calculate this piece right here. I'm going to actually figure out what this is. And remember how I was saying you might get to a point where you don't need all that business anymore. Let's try it. Negative 3 plus 1 should be a negative 2. So I have x to the negative 2 power, and that will be divided by, ready, a negative 2. Well, there's no fraction to flip here. This is really just the same thing as 1 divided by negative 2, which is a negative 1 divided by 2, and that x comes down and becomes a positive 2. I could write that better. Here, a positive 2. And here's my plus c. And that, what is that? There's a hanging equal sign out here, Ms. Shatra. Is that okay? In this case, no. I want to say that f of x is that. Do you see what I'm saying? He asked me to find f of x, so I need to write down what I found. I found the antiderivative, and the antiderivative of a function is just f of x. So here's a little note for you. You want to have this somewhere. The integral of a derivative is the original function, okay? And this rule is so important. It's called the fundamental rule. It's called the fundamental theorem of calculus. And there's a little bit more to it, so I'll be reintroducing it in a later section, okay? So then right now, if I know what f of x is, and it looks ugly, so I'm just going to rewrite it. I just want it to look pretty. This is negative 1 over 2x squared, and then there's a plus c. But he told me right here that when x is 1, so f of 1, I'm going to plug in, ready, this, 2, 1, a squared plus a c. He told me to look when it was 1, right? But here's the thing. He told me what f of 1 was. F of 1 is 3/2. So I'm just going to write this 3/2 down. And over here, I'm going to simplify this a little bit. Negative 1 over 2, because right, 1 squared is 1, and 1 times 2 is 2. And here we go. Now I'm going to add 1/2 to both sides. I'm going to add 1/2 to both sides, and I'm going to end up finding out that c, I mean, if I had more room here, just make it a little bit smaller, there. C will equal 3/2 plus 1/2 is going to be 2. And so my original function has now been found, and it is negative 1 over 2x squared plus 2. That's a lot of 2's. I'm sorry about that. I wish that we had an example where there wasn't a bunch of 2's in it, but you know, it's a coincidence. There you go. All right. Now, this last example is so fun because again, it comes back to this fundamental theorem of calculus. Basically, what he's saying is that those things cancel out. My answer to this question will be 5 times the square root of x minus 1 over x squared. I don't need to do the work, right? I'm putting parentheses around this because when I was a student teacher, somebody told me never to use the phrase cancel out, but you guys use it all the time. So I'm not sure why I'm not supposed to say that they cancel out. I'm going to say this. Remember this rule where the radicand just pops out? Well, by the way, that x is called the radicand. Yeah. You remember? I taught that a while ago, didn't I? That was a hot minute. All right. So the integrand, it just pops out, right? It just pops out. ddx and an integral, they undo one another, just like a square rooting with a square undoes one another, all right? So it's not enough in this section to just teach you how to do the antiderivative. Let's actually do some applications, like right now in this thing. Right now, if I had the position, I take the derivative, I get velocity. I take the derivative again, I get acceleration. So if they give me acceleration, I will do the integral and I will get velocity. I will do the integral and I will get position. Okay, so those are the rules that we're talking about right now. And yeah, there's a lot of notation I would kind of like to take the time to do. And you know how I am. The integral of, ready, acceleration will give me velocity. That's what I'm talking about right there. You see what I'm saying? That looks good. That notation looks so good. I'm glad I took the moment to do it. What are we using for position? S? Here we go. Okay? So the integral of acceleration gives me velocity. The integral of velocity gives me position, and I'm a happy camper now. So if he told you what what the acceleration was, then find that velocity equation. Ready? The velocity equation is the integral of acceleration and with respect to t. Thank you very much. And so I have the integral of 4t minus 3. And now do you know how to take that integral? Sure you do. T should be squared because it had been to the 1 power and I added 1 to it. There was a 4 out in front and that new power should be in the denominator. The integral of a constant will be just a linear equation. And then here is my plus c. All right, so again, let me say that velocity is going to be 4 divided by 2 is 2t cubed squared minus 3t plus c. That's not the full thing though, right? I haven't found what c is, and I'm already running out of room here. So let me put this off to the side. So v of t equals 2t squared minus 3t plus c, and that constant can be found like this. Ready? Initial conditions. All right, there's a 6. V of 1 is 6, and I'm supposed to plug that one in, and that's how I find that c. So this is a 1 squared is 1 times 2 is 2 minus 3 times 1 is 3 plus c ends up being 6. That's just 6 equals negative 1 plus c. I add 1 to both sides, and I get that c equals 7. Okay, so I don't even want to write that here. What I want to write down for my answer, what is v of t? V of t is going to be 2t squared minus 3. Well, I'm looking at finding the position function, and I'm seeing that I'm going to get some fractions. So I'm going to move off to the side here, okay? And I'm going to do problem. This is number 12b, okay? This is 12b, and I just don't have enough room in that spot. So good luck with you guys if you're taking it in the notes. Make sure you do it really small. My original function is here. All right, there's my function, and I want to do the integral. So I'm saying that I'm throwing an integral dt and an integral dt, and now I'm going to move forward, okay? So the integral of velocity is position, so s of t will end up being, ready, 2, and here is t goes up by a power and is divided there. See, I told you I was going to get a fraction. There's a minus sign here, and this is t goes up by a power and becomes a fraction. And then, this last piece is not a lot easier. The integral of 7 is going to be just 7t, and then there's plus c. So that is my new function, s of t. And you know, when you're doing this work, if you're trying to make it look nice, does it bother you that there's a c here? And then there's a new c here. For some people, it kind of like triggers them. And so I'll tell you that in notes, in answers, the answer keys for our professor, he might do this, like, hey, what is that? He's just saying I'm finding a constant. This happens to be the first constant that I'm finding. And then he'll do it right here. He'll say this is the second constant that I'm doing. I didn't learn like that. It doesn't bother me that c is a different number in different parts of a problem. So I just let it go. I'm not going to put any sub numbers here because this is the second constant that I'm finding. But if you look at his answer keys, you will see, you know, those sub numbers, because I found this c and now I'm finding a new c, and then that's different from some other c. So by using those sub numbers, so sub numbers for different c's. Not me. I'm not going to do that. I'm not putting those down anymore, okay? But I was given some initial conditions, and if you look back at your paper, you'll see that it was s of 2 equals 5. So I can say that this is 5, and I'm supposed to plug in a 2. I'm looking for this c. It just happens to be the second c. What do I get? Sorry. 2 times 2 times 2 is 8. 8 times 2 is 16. 16 is divided by 3. 2 times 2 is 4. Times 3 is 12. Divided by 2 is going to be a negative 6. And 7 times 2 is 14. And there's my plus c. Negative 6 plus 14 is really the same thing as 8. I'm going to write that down. And you know what? I'm going to subtract, like, you know, a little bit slower here because I hate fractions. So I get a negative 3 here, and this is a 16/3 plus c. And now I'm going to minus 16/3 from both sides. And so C will end up being -3 minus 16/3. This is really the same thing as 9/3. So that's really a -25/3. And that's what C is. So I can come back up here to the beginning and I can say that S of t, the specific S of t that I took the derivative of, was going to have been 2t cubed over 3 minus 3t squared over 2 plus 7t minus 25 over 3. Ta-da! There it is. That's the one that he was asking for. Ooh. Are we done yet? Nope. Looks like we got one more. Here it is. And I got room, so I'm going to do it. Given that on Earth, the acceleration of an object due to gravity is approximately -32 feet per second squared, negative indicates downward motion, develop the equation for the velocity of the object and the equation for the position of the object. These are generic formulas that we will then be able to use in physics. So let me recap that we were given that the acceleration is -32. Okay, and I'm not sure how I'm going to get to the answer to that quickly, so I'm just going to cross this out. And I'm going to say that acceleration is -32. And I want to find, ready, the integral of that. Aha. And the integral of that, here's where I'm going to put down the integral of acceleration is velocity, and the integral of -32 is -32t plus a c. Aha. And then I have been given some initial conditions. I have? Well, yeah, you know, anytime I'm doing a physics problem, I will be told that the initial velocity is something. And normally in physics, they call it v sub 0. Initial velocity is v sub. So what is this constant then? Here? It is the initial velocity. Whatever velocity you've been given, you're gonna use that initial velocity with the antiderivative of acceleration to find out that your function will be this, right? Take that initial velocity and add it to whatever time you are using in your problem. Same thing over here, by the way. I don't think I can get to this answer so quickly, so let me try like this. The integral of v of t dt will be the integral of -32t plus that initial velocity and dt. And yes, sometimes I forget my parentheses. I'm sorry about that. So the integral of velocity will be position. And the integral of -32t will be -32t squared divided by 2. And the integral of v sub 0, remember that's just a constant, is v sub 0 times t. And then there's plus a c. And I want to clean that up just a little bit and say there's a -16t squared plus v sub 0t plus c. Well, the initial position it's that. Well, it's just like any other, function. When you shift up or down, you do it by adding or subtracting at the end. So S of t is really -16t squared plus v sub 0t plus S sub 0, meaning my initial position. And we should use these functions, and yeah, maybe I should put that on the mega cheat sheet in those physics problems in the rest of the homework. I wanted to come back and show you that equation as they use it on the internet. If I talk about the position of a falling object on Google, I search for that. I'm looking at the falling object model. Varsity Tutors pops up, and here we go. There's the formula that I just came up with. And so now you know where this formula comes from. It comes from calculus, and we use it all the time. Now they're saying h of t because they want it to be a height, and then h sub 0 is going to be your initial height. So I'm saying that S sub 0 is your initial position, but you might want to write down this, also known as an initial height. Okay, and hopefully that'll help you actually do the problems in our homework.